if the energy stored in an inductor is 2 joule, okay, if the energy stored is 2 joule, then it carries a current of 1 ampere. Oh, so it should be if it carries a current of 1 ampere. If the current is 1 ampere, then the energy stored in the inductor is 2 joule. And now they ask, find the energy that will be stored, the new energy that will be stored in the same inductor when the current is 2 ampere. Now, the new situation is if you have 2 ampere, what will be the new amount of energy stored? Okay, this is actually quite, I think quite easy. I think if you use your logical sense, you should be able to do it. Okay, but the idea is like this. U is equals to half Li square. So you know that this should be the old situation. And you know that the new situation will be U prime is equals to half L prime I prime square. Okay, so if you find the relationship between the new and the old, you can find the relationship by dividing the new equation by the old equation. So you get half L prime I prime square divided by half L I square. Okay, so now what you need to do is you need to find the relationship between the new self-inductance and the old self-inductance. You need to find the relationship between the new current and the old current. Okay, so for this situation here, you are using the same inductor. So if you are using the same inductor, then that means the shape is the same. The material is the same. So if you're not changing the shape, you're not changing the material, then come back to the statement earlier. If you change nothing of this, then the self-inductance should remain constant. It doesn't change because your current changed. Your current doesn't affect your self-inductance. If your shape of the inductor never changed, if the material you insert inside inductor never changed, then the self-inductance will never change. It only depends on these two main factors only. So if these two main factors remains the same, so you can end up with a conclusion that L prime will be equals to L. In other words, L never change. And because you know that, you can cancel out the new L and the old L. You can cancel out the half, and you can see that it's just a relationship between the new current square divided by the old current square. Or you can print it like this. Okay, so you know that the new current is 2. You know that the old current is 1 square. Then you arrive at the answer, which is 4. Let me keep everything vertical. Is equals to 4. So therefore, you can see that new energy stored is equals to 4 times of the old energy stored. The old energy stored is how much just now? 2 joule is the old energy stored. So you can substitute in 2 joule. Then you get the final answer to be 8.0 joule. Okay, so that's how you do it. It's just a ratio question. You need to find the equation that relates between the current and the energy stored. And this is the equation. You write the old equation, you write the new equation, then you compare the equation by dividing the equation. But first, you have to determine the relationship between the self-inductance, and you know that they are the same because the shape never changed, the material never changed. So the L, new L is equal to OL, cancel out, so you're left with just the current divided by the new current divided by the old current squared. So substitute in, you get the relationship between the old energy and the new energy to be a factor of 4. So now you can just substitute in the old energy to get the new energy. Okay, a very direct question. It's just a ratio question. Okay, so this question here wraps up everything I want to discuss regarding self-inductance. So that's it for this video. In the next video, we are going to discuss mutual inductance.